Welcome to section 9.6. This is the 77th session of the CISSP exam prep series. In this session, we'll explore the systems that run our physical world. We'll answer several questions. What is an industrial control system? What are its main forms? And how do they scale? How do these systems talk to each other? Why have they been so poorly secured? And how do you harden them? Why does this matter beyond the exam? Because these systems do not just move data. They open valves, spin turbines, and run assembly lines. Picture a regional water treatment plant. A compromise here does not leak a spreadsheet. It can taint the water supply for a whole city. On the job, you may inherit decades-old control gear that was never built with attackers in mind. Protecting it is where digital security meets physical safety. So what is an industrial control system? It is a computer-based device that manages industrial processes and machinery, a category often called operational technology. You find these systems running manufacturing lines, power generation and distribution, water and sewage handling, and oil refining. They are the quiet brains behind heavy industry. Think of the nervous system of a factory, sensing conditions and firing the signals that make the machines move. What are its main forms, and how do they scale? There are three you must know, and they climb a ladder of scale. A programmable logic controller is a focused, single-purpose computer that automates one electromechanical job, like driving a stretch of an assembly line or a giant stadium display. A distributed control system links several such controllers within a limited area, spreading control elements across a plant floor, while a central location issues commands and gathers status. And a supervisory control and data acquisition system stretches that reach across vast geographic areas, using a human-machine interface so operators can oversee everything, and it can command those lower controllers beneath it. Here is the clean way to hold it. One controller might run a single transformer, a distributed system manages a whole power station, and the supervisory system watches over an entire power grid. Think of a single traffic light, then a coordinated intersection, then a control room steering traffic across an entire region. How do these systems talk to each other? Largely through a long-established industrial protocol that has become a de facto standard for connecting devices on the plant floor. It gives machines from many different manufacturers a common language to exchange data and commands, which is essential in these mixed environments. That very openness is a double edge. It delivers the interoperability the industry depends on, but an open, widely understood protocol is also easier for an attacker to speak. Think of a universal set of hand signals every worker on a site understands. It keeps the crew in sync, but a stranger who learns the signals can start issuing orders too. Why have they been so poorly secured? Because their static design and bare interfaces once seemed protection enough, so little real security was built in. For years that assumption held, until it did not. There have been serious, well-known compromises, including a landmark piece of malware that planted the first known rootkit inside a control system at a nuclear facility. That was a wake-up call, and vendors have since started adding protections. Yet in practice, many of these systems remain weakly defended, rarely patched, and full of older versions that were never designed with security in mind. Think of a factory built long before anyone locked the gates, now sitting in a neighborhood where the threats have very much arrived. How do you harden them? You apply solid, familiar, security discipline tuned to their reality. Isolate the control networks from general traffic, restrict access both physically and logically, and allow only the essential applications to run. Change the default credentials that ship with the gear, and log all activity so you can see what happened. But there is a crucial shift in priorities here. In ordinary IT, we often lead with confidentiality. For operational technology, the top concern is availability, the uninterrupted flow of real-time control signals, because a paused signal can mean a physical disaster. A set of recognized industry and government standards exists to guide this work. Think of the difference between guarding a filing cabinet and guarding a moving crane. With the crane, the one thing you can never allow is for the controls to freeze mid-lift. So let's bring it together. An industrial control system is the computer brain behind physical processes, the heart of operational technology. Its three forms scale up a ladder, from a single controller to a distributed system across a plant, to a supervisory system spanning an entire grid. A common open protocol lets mixed devices talk at the cost of easy access for attackers. These systems were long left insecure, as real-world compromises proved. So you harden them with isolation, access limits, credential changes, and logging. And above all, you protect availability. Because here, a frozen control signal is not an inconvenience, it is a hazard. The MCQs covering all the topics and concepts from this session are available on RooCloud.com. Practice the chapter-specific MCQs before moving on to the next session. Thanks for watching. If you have any questions or feedback, post a comment below or email us. I will see you in the next session.